So we have split the mesh regions, and we can clearly see there are three regions called domain 0, which is a water block, and domain 2, which is the air block, and the solid, which is a region between the two fluid domains in parallel view. So if you go back to the demo folder, you will see there will be the 0 folder that has been created by using the split mesh region commands. And when you open it in the 0 folder, there are 3 domains that have been defined, and there's a cell-to-region file. So cell-to-region file is really about the cells, so the meshing mesh cells for all the 3 domains. And when you go to each specific folder, you will see the cell-to-region is actually defined. Depending on which region it belongs, it has the boundary conditions that has been inherited from previous block mesh, and also here the interfaces between the domain and between the domain. For example, this is domain 0, so there will be interface between the domain 0 to solid. So the split mesh regions will automatically build the interfaces between regions. We don't need to define it, and it will also create a name and the type for us. So next step is to tell the solver or the software which regions is solid and which region is fluid. So we need to define the region properties and the constant folder. Now we go to the constant folder. The constant folder has been created, right, when we do the block mesh, and now after splitting mesh, it also creates the 3 folders and the cell-to-region. So this cell-to-region is very similar to the ones in the 0 folder. And the 3 domains, there's also the polymesh, which means the boundary conditions and also the meshing information for that. But that's only geometric information, and we also need some like physical information. And before doing that, we need to define the region properties to clarify, or let the solver identify which one is solid and which one is fluid. So we can go any tutorial examples and CHT multi-region simple form. We go this and say if we will have so we have the region properties here, and also we need to define the gravity. So the CHT multi-region for simple form can use the buoyant force during the calculation, which means the temperature change can introduce the change of density, and that will introduce some extra gravity forces by doing this. So we copy these two, and then we paste it into the constant folder. So constant folder here. Now we open the region properties file, and here the region has been from the previous folders. They only have the air and porous without any solid, but now we have the both solid and fluid, right? So I need to define here, we have 2 fluid domains called domain 0 and domain 2, and solid, we have the name of solid, and that's all. So that is our definition of the regions, and the solver will identify it. Yes, the domain 0 and 2 is fluid, and solid is the solid. And then we go to the gravity. We just have a quick check if we have the gravity file. So the gravity file have a dimension of this. So 0, 1, -2. And we only need to check about our dimensions. So we have the y direction. So we think the gravity will point into the negative y direction. So we need to define here as 0, -1, and 0. So the value is really define the directions of the gravity. Okay, these two are the definition for the region properties and the overall gravity field. And also, we now need to think about the fluid region. So in the fluid region, we want the fluid flow to be very laminar flow, and that is usually need to be defined in the constant folder. So again, we can go to any constant folders here, and we need to find the so turbulent properties only for the fluid regions, right? Only for the domain 0 and domain 2. Then we now need to check about if we have any fluids in the example. So we have. So we only need to have the turbulence properties to be defined for the fluid 1, for the domain 1 and domain 2. So we copy here, and we have quick check if it has. So this is not the fluid field 1, 2, because it uses a turbulence flow or turbulent flow with K epsilon, but we want a laminar only. So we change it to laminar. So laminar is what we want, and after doing that, that is turbulence properties for domain 0, and we directly copy it to domain 2. So that's fluid flow. So the solver knows that the fluid flow will laminar for both fluid domains. And remember, we not only think about the fluid flow properties, but we also think about the thermal properties, right? So now we need to define the thermal properties for both fluid domains and the solid domain. So the name for this is thermal physical properties. Again, we go back here and we will see the thermal properties for air. So we have the air, right? So domain 2 is really for air. So if you still remember, the above is domain 2. I can directly write here. So this is 2 and this is 0. So that's the 0 for water and 2 for air. So we go back here, we have a quick look at the domain 2 thermal physical properties. We open it, and we would say it has the thermal type. We have the mixture, which means the properties of that, and we just need to have a change here. For what change? Because we want the calculation to be very simple, so we can copy this and replace all this here. Use our definitions. So our definition is quite simple, if you see here, and the most important is we think the air properties. So the density of the air didn't change during the calculation, and also there are some transport properties about mu, Prandtl number, and also we define the rho. So the density is directly to be defined as 1.2 kilogram per meter cubic. And the thermodynamic, which has the specific heat capacity as a HF. So that's all for the thermal or physical properties. And after doing that, remember we have two fluid domains, right? The other domain is the water. So that is domain 0. So domain 0, of course, we need to change all the parameters here because the water has different thermal physical properties. So we copy here and we just replace all this. There are some difference if you see the exact values, because specific capacity significantly increase for the water compared to air, and the mu is also different, and of course density of water is much higher. So the air is 1.2 and for the water it is 1000. Again, our mean is to define a constant density for the fluid domains. So that is the physical properties definition, and also the fluid flow definition and the constant folder.